Hello pharma aspirants, welcome to online GDC classes. So we are in the path of Target Pharma 360 degrees. Okay. So in this series we are going to discuss about different types of the MCQs related to the each and every subject. So especially today in our pharmaceutical analysis subject we are going to have the discussion on the some of the MCQs related to the NMR spectroscopy. Okay. That means you know NMR means nuclear magnetic resonance spectroscopy. So in this some of the few questions have been included in this today's session, and these MCQ series are going to be included in this Target Pharma 360 degrees. Okay, this MCQ series we have introduced in our GDC English channel, which is going to give you more help or more knowledge in cracking the competitive exams like MRB, RRB, Drug Inspector, Telangana DI, 𝘎𝙬𝙎𝙬𝙬. Okay, so some of AIIMS Pharmacist exams, all these things you are going to have some of the key concepts are also we are going to discuss in this MCQ series. Okay, so let us go into that. The first question related to the NMR spectroscopy. We know that NMR spectroscopy means nuclear magnetic resonance spectroscopy. So the first question here is the NMR spectroscopy, which energy is absorbed. That means what is the energy absorbed here? What are the source of the radiation we are going to use for this NMR spectroscopy, nuclear magnetic resonance spectroscopy? So options they have given: cosmic energy, vibrational, radio frequency energy and rotational energy. So in this if you easily select what is the correct answer, but let us have the basic concept that whatever the electromagnetic radiation it is there, so it is going to be divided into different types of the radiations based on the wavelength. Okay, so cosmic rays whenever we are going to see, which are going to have the shorter wavelengths but which are having the very high energy, okay, high frequency also. Whereas if you are seeing about the radio waves, these are going to have the longer wavelengths but less energy these are going to possess. Okay, so in case of the NMR spectroscopy, whatever we will give the electromagnetic radiation, that is nothing but the radio waves we are going to use. So those radio waves are going to be generated by radio frequency generator. It is going to be used. So in this given option, if you see the cosmic energy means cosmic rays we are going to see, so that is not the right answer. Vibrational energy means we are going to come across in case of the IR spectroscopy, and rotational energy means we are going to see in case of the microwave spectroscopy, and only the correct option, that is radio frequency energy, so which is going to give you the radio waves. Okay, so thereby the nucleus it is going to be coming in the resonance state. Okay, so option C is the right answer for this question. Second question, if you see the radio frequency energy, whatever it is there, that is absorbed in presence of which of the following field. Okay, so in presence of which of the following field, that means in the NMR we are going to use the magnetic field in order to keep the nucleus into the resonance state. We are going to use the very powerful magnetic, that's why it is nuclear magnetic resonance. Okay, so magnetic field we require. So here whatever the radio frequency energy which is going to be generated, that is going to be absorbed in presence of which of the following. In order to absorb that radio frequency energy, we are going to have the strong magnetic field there. Okay, so option A, magnetic field, it is going to be the right answer. B, electric field, no. Rotational, electrostatic, nowhere. These are going to be suitable for NMR. Okay, only the option A, that is the magnetic field, it is going to be the correct option. Third question, if you see the ratio between the nuclear magnetic moment and angular moment. Okay, so here the question is related to a formula. The formula which is nothing but the ratio between the NMR nuclear magnetic moment it is there. Okay, so that magnetic moment it is going to be and angular moment. Okay, so this magnetic moment and angular moment, whenever we are going to take that ratio, it is going to be called it as magneto-gyric ratio or gyromagnetic ratio, we are going to call it as. Okay, so in the options they have given magneto-gyric ratio, precessional moment, gyrometric ratio, so it is somehow a spelling, so that is not the correct one. Rotational moment, nowhere these two are related. Okay, this is not related to the NMR. Only magneto-gyric ratio. This is also called as gyromagnetic ratio also. So option A, it is going to be the right answer here. Okay. Next, which of the following is NMR inactive? Okay, in order to know which compound it is going to give you the NMR signal, even though you put the sample in the high magnetic field and we are going to give the radio waves as the energy to that molecule, some of the molecules are not going to absorb that radiation. Why? Why? Because there is a clause for NMR absorption. So what is that? Whenever any electron, that means radio waves, are going to be absorbed, means the clause is nothing but either mass number should be an odd thing or atomic number, either mass number or atomic number. Any one of these should be an odd number. Then only the absorption of this radio waves, it is going to takes place. Then only the nucleus, it is going to be changing its spin state. Okay. So that is the condition for NMR absorption for any molecule. So in this they have given option C12. C12 means it is going to be the mass number. Here this is the mass number. Mass number is even here. So if you see the atomic number of carbon, that is 6, that is also even. So this is NMR inactive. Okay. So in that case, you can say that NMR inactive means C12 is NMR inactive only. Okay. So if you see the O17, oxygen mass number 17, this is a mass number, odd mass number. So it is NMR active. Okay. And S33, sulfur, this is also mass number 33, that is odd, this is also NMR active. And P31, phosphorus 31, this is also odd mass number. So all these three are NMR active. They can give the NMR signal. Only C12 cannot give the NMR signal. Okay. So that's why isotopes we are going to use C13 NMR. Like that we are going to use in order to get the NMR signals. Okay. So they have asked NMR inactive. So obviously A is the right option for this question. Okay. Now let us move to the another question. Consider the following isotopes. Which nuclei will be NMR inactive? Again the question related to the NMR inactive only. That is not suitable for the NMR measurement. That means among these atoms, which molecule, that means each molecule is having these number of atoms. So due to at least one atom, it is going to give you the NMR signal. If all these are not suitable, that means which are not having any type of the odd mass number or odd atomic number, then definitely you are not going to observe the NMR signal. Let us see which type of the molecule in the given options is NMR inactive. So if you see H2, this is NMR inactive, C12 is inactive, N14, okay, nitrogen, even though the mass number is even, but the atomic number of the nitrogen is odd, 7, right? So this is going to be the NMR signal you are going to observe. O16, definitely it is not going to give you the NMR. And coming to the option B, but the question is completely NMR inactive. Okay. So H2, no NMR, C12, no, N15, okay. N15 means atomic number, you can get it, NMR signal. This O17 means mass number, this is odd, mass number odd, okay, no need to go for, this is NMR active only. Now let us see C12, this is NMR inactive, this is also NMR inactive, okay. So option C, it is going to be the right option for this question. C12 NMR inactive, O16, but nickel 61, this is the odd mass number, so this is NMR active. So among the given options, C is going to be the suitable, because which is a NMR inactive. Okay, atomic number is even and mass number is also even, then you are not going to observe any NMR absorption. Okay. Next question, which compound does not show anisotropy in the NMR? Okay, anisotropy. So you should learn first what is anisotropy. So anisotropy and chemical shift, these are correlative. Okay, these are interrelated actually. So let us see first of all what is anisotropy, then we will try to answer this question. So they have asked which compound does not show, that is the anisotropy in NMR. benzene, ether, acetylene, acetic acid. So among this, let us first see what is anisotropy, then we will come to know what is the molecule which cannot get the anisotropy. Okay. So if you observe the what is anisotropy in this means the nuclear magnetic resonance, that means where you are going to see the signals due to the absorption of the radio waves, right? They are kept in the high magnetic field. Under the high magnetic field we are going to use, and this high magnetic field, it is going to be causing the spinning of the nucleus. Okay. So the high magnetic field, it is going to cause the spinning of the nucleus. Spin quantum number, it is going to be changing. Okay. So thereby you are going to see the nucleus is kept in the resonance state. Okay. So the spin, it is going to change. So in this, if you see the anisotropy, so what is called anisotropy means it is a property of the compound which is going to tell you about the somehow the information related to the chemical shift. Okay. So we know that in the NMR, the chemical shift, it is going to be taken on the x-axis, right? So the chemical shift values are going to be actually if you see the NMR spectra, this NMR spectra you are going to see from the like this. So chemical shift values are going to be increasing from the right to left. Okay, 0, 1, 2, 3, 4 up to 14 or like that only. Okay, so in the proton NMR if you are talking about, so then immediately you are going to see the peak that is related to the tetramethylsilane, that is nothing but the reference peak. Okay, the reference standard we are going to use, and this is the number of peaks whenever you are going to observe for the chemical shift. You are going to see that means the towards the TMS, away from the TMS, different types of the peaks we are going to observe based on the type of the molecule. So this anisotropy, what it is going to tell you is, because it is going to give you the information related to the shielding and de-shielding effects. Shielding and de-shielding effects in the NMR. Okay, that means it can be best explained in this benzene ring. Okay, benzene ring means you are going to see the pi electrons. Okay, let us see in the blackboard itself. So in this, if you observe in case of the benzene ring, you are going to see, if you are able to see the blackboard, then you are going to easily understood. So on the benzene ring, there are pi electrons are going to be observed. Okay, so in this pi electrons, that delocalization of this pi electrons, it is going to takes place. You know that. Let us say this is the benzene ring. Okay, and we are going to see the hydrogens like this. Okay, so whenever this benzene ring, you are going to see the hydrogens are going to be present. Due to these hydrogens, we are going to see the pi electron. Double bonds are there means pi electrons are definitely we are going to observe. So these pi electrons are going to be causing the delocalization of the electrons. Okay, that means delocalization of the electrons, it is going to take place, and you are going to see the due to the external magnetic field, the shielding of the protons, it is going to take place, or sometimes de-shielding of the protons it is going to cause. So inner side, that is okay, it can be maintained, but whatever the external magnetic field we are going to apply to the molecule. Okay, so in order to make the nucleus into the resonance state. So if you are talking about the proton NMR, so when these hydrogens are going to be playing a key role. If you are talking about the carbon NMR means we are talking about the carbons. Okay, so just imagine the proton NMR, the whatever the hydrogens are there, the pi electrons are present in that. So these hydrogen are going to cause the delocalization. Thereby you are going to see the shielding and de-shielding electrons, it is going to take place. So this is a chemical shift. Okay, so chemical shift values are going to be high. So this is going to be the actually initially if you see the TMS peak here. Okay, So TMS, you are going to see the 0 for chemical shift value, it is going to be the 0. So then you are going to see the different peaks in the NMR. So actually in the NMR you are not going to see the bell shaped curve, straight lines you are going to observe, but you are going to see the peak splitting there. That is due to the non-equivalent hydrogen atoms present on the neighboring molecule, neighboring atom. Okay. So generally if you are talking about NMR signals, means these are very straight signals, but splitting of the signals, it is going to take place because of the neighboring hydrogens only. Okay. So this chemical shift, it is going to be related to this shielding and de-shielding, means how the electrons are going to cause this shielding and de-shielding, that is depending on the these pi electrons. Okay. So you are going to see the shielding effect towards the TMS signal, and here you are going to see the de-shielding effect. That means in the de-shielding effect you are going to see the more chemical shift values. Okay. So whatever the electrons are there, they are going to be de-shielded here, and shielding effect, it is going to be causing the chemical shift values towards the very lower side. Okay. So if you observe the anisotropy in detail, then you will see how this anisotropy in the benzene ring, it is going to be movement, how the pi electrons around this benzene ring, it is going to cause. Okay. So like the external, if you don't apply the external magnetic field, then you are not going to see any anisotropy. Whenever we will apply some of the force or some of the magnetic field externally, if you apply magnetic field, okay, so then what happen, the external magnetic field, there is a movement of the electrons around the benzene ring, it is going to takes place. Okay. So that movement of the electrons, whenever you are going to see, will oppose this applied magnetic field. Okay. So this is only with respect to the interior of the ring, that means due to the benzene ring, whatever it is there. Okay. So due to the interior of the ring, it is going to be with respect to that. So these movement of the electrons, it is going to oppose the external magnetic field. Okay. So this external magnetic field, whatever it is there, that means not related to the interior of the ring, whatever the external environment it is there. Okay. So with respect to that exterior of the ring, exterior, whatever the outside environment it is there, the movement of the electrons reinforces this external magnetic field, right. So the delocalization of the electrons, first it is going to take place, afterwards the movement of the electrons, it is going to cause the anisotropy. Why means because of this opposition. So if you are any type of the energy we are giving outside, what we do, our defense mechanism will try to stop it. In the similar way here also, the molecule, it is trying to stop that magnetic field. Okay. So all this is going to happen because of the pi electrons. So it is going to be best, here they have explained with the benzene ring. So whatever the protons, whatever the hydrogens of these aromatic compounds are there, okay, so they become de-shielded with respect to the conventional protons. Okay. And thereby the absorption, it is going to be towards the downfield. So de-shielded means downfield, that means the chemical shift values are going to be very high. These are very far signals we are going to observe because of the opposition of the force. Okay. So due to that only you are going to see that anisotropy. This is called as actually magnetic anisotropy. Whenever magnetic field is applied, due to the external magnetic field, the electrons are going to oppose that external magnetic field. Okay. So especially pi electrons, it is going to take that role. So thereby you are going to see the anisotropy in some of the aromatic compounds. So in this anisotropy, again so many types are also there, don't go in depth of this. Now here they have asked which compound does not show anisotropy. So aromatic compounds as well as some other compounds are also, these are going to exhibit this anisotropy, and here they have given the options benzene Definitely, just now we have seen the example. It exhibits the anisotropy either means C2 diethyl ether, right? So C2H5. So actually diethyl ether, whenever you are going to see, so due to the symmetry C2H5 it is there, so thereby it is not going to give you any type of the anisotropy. So imbalance it is going to be there. So acetylene and acetic acid, here you are going to see the CH3COOH, acetylene, okay. So DC double bond C you are going to see. So definitely you are going to observe the anisotropy in these 3 pi electrons are there, but whereas in case of the ether means actually you are not going to see any type of the pi electrons there, right? All very, very strong sigma bonds you are going to see. That means CH2 diethyl ether you are going to observe for this, okay. So all sigma bonds you are going to see, C and C, like this you are going to see the in diethyl ether. So that's why no anisotropy you are going to see in case of this ether. No case of the pi electrons we are going to observe there. Next, which type of the nuclei will give the NMR spectra? Okay, this already we have discussed about this part. Nuclei having the either odd mass number or odd atomic number. So options: odd mass number, no, that is the right answer. NMR, that means NMR active they are going to ask. Odd mass number, definitely you are going to see the NMR signal. Even, no. Odd and even mass number, none of these. Okay, no, this is not the right options. Okay, only A is going to be the right answer. Next question, which type of the quantum number is preferred in the NMR spectra? Quantum number, okay. So whenever you are going to observe the nucleus in the resonance state, then the spin state of the nucleus it is going to be changed, then only the nucleus is going to be called it as in the resonance state, okay. So in that case, a quantum number related to its spin, it is going to be affecting a lot. That means it is going to have either a fractional quantum number or integer quantum numbers are also there. So here they have asked which type of the quantum number is preferred in NMR spectra. Generally, which type of the quantum number is preferred, okay. So which is related to the spin only we are going to talk in the NMR. So automatically Planck's no, where absorption no, azimuthal no, spin quantum number, okay. So this spin quantum number only it is going to be related to the NMR spectroscopy, right. Next question, nuclei with odd mass number give which type of the charge distribution? Okay, so whenever we are going to apply some magnetic field to the molecules and radio frequency it is going to be given as energy, there is going to be a charge distribution, it is also going to occur in the molecule. Here we are going to see the nuclei with odd mass number give which type of the charge. That means the nuclei having the odd mass number or even mass number or odd atomic number, even atomic number should be there, but sometimes we are going to see any one of this, and isotopes mostly we are going to use in order to get the NMR signal. And here they have given symmetrical charge distribution, asymmetrical charge distribution, binomial charge distribution, polynomial charge distribution. Whenever odd mass number it is there, you can say that you are going to see the charge distribution either symmetrical or asymmetrical only, okay. So let us see different types of the spin quantum, these are going to be spin quantum numbers for this, okay. Thereby you will come to know how this distribution it is going to occur. Whenever the spinning it is going to takes place because of the radio frequency, so it is going to related somehow to the composition of the nucleus. How? Odd mass nuclei if it is present, then that means what? Those are having odd number of the protons, the mass of the protons or neutrons is odd, okay. So the total of the protons and neutrons it is going to be the odd number, which are going to have the fractional quantum number. Fractional spin quantum number, you are going to see that. So examples like spin quantum number we are going to represent with the I. So like this 1 by 2 or 3 by 2 or 5 by 2. Like this spin quantum numbers you are going to see. That means odd mass number nuclei which are going to have this fractional quantum numbers. So like this examples proton, C13, okay, F19. So all these are the odd mass numbers. For that you are going to see the 1 by 2 as the spin quantum number, and B11 boron 11 it is there. For this you are going to see the spin quantum number of 3 by 2, whereas oxygen 17 isotope you are going to see the spin quantum number of 5 by 2. So this is related to the odd mass nuclei, whereas even mass nuclei. Even mass nuclei means what? It is composed of either combination of the protons and neutrons is even, but any one of this is going to be odd, right? So 7 protons, 7 neutrons if you take, total will be 14, but odd protons, odd neutrons are going to be there. So this is the case we are going to see. So like this you are going to see the H2 hydrogen, if it is there then the mass number is 2, and nitrogen 14 it is there. So even the atomic number is 1, the atomic number is 1, but mass number is 2. Okay, so what is the condition for NMR absorption? Either atomic number or mass number should be an odd number. Okay, so for this also you are going to see the NMR absorption, and you are going to see for the even mass numbers you are going to observe the quantum number as 1, integer values 1, 2, 3 like that. Okay, so even mass whatever which are going to be observed, for these even number of protons or neutrons are present. Okay, that means atomic number is even and mass number is also even. In those cases you are going to see the 0 spin, no spinning at all. That means spin quantum number is 0. Okay, in which type of the samples, like C12 and O16. So in these nuclei you are not at all going to see the NMR absorption. So this spin quantum number, whatever these are going to be either fractions or integer values are there, generally these are going to have the charge distribution. Okay, so spin with 1 by 2, that means like this, I equal to 1 by 2, generally they have a spherical charge distribution, and their NMR behavior it is easy to understand. So the question related, that is, what is the nuclei with odd mass number? Okay, so odd mass number distribution, it is going to be somehow asymmetrically it is going to be done. Okay, so even mass nuclei means you are going to see the integer values 1, 2, 3 like that. Okay, odd mass numbers means you are going to see the asymmetrical charge distribution. So in this way you can remember that. Nuclei with, next question, nuclei with even mass number. Okay, whatever the question we have seen previously, that is opposite to that. Odd mass number will give you the asymmetric charge distribution, even mass number will give you the symmetrical charge distribution. The options, let us see: asymmetrical, symmetrical, integral value, okay, binomial distribution. So integral value distribution means 1, 2 integers, complete numbers we are going to see, but these are actually called as symmetrically distributed. Okay, so that is the exact right answers. Next, precisional frequency is obtained at which state? Okay, so whenever we will give the radio waves as energy to the molecule, so the frequency of the radiation it is going to be there. So that applied frequency, whenever it equals, whenever it matches to that precisional frequency, then only the absorption of the NMR radiation it is going to takes place. So here the question related, precisional frequency is obtained at which state? Options: excited state, spin state, ground state, magnetic state. No, actually if you see in the absorption of the radiation it has to takes place means then only the natural frequency equal to precisional frequency, then only the spinning of the nucleus it is going to takes place. Ground state, we are nowhere talking about the precessional frequency. It is as plain as that of that. Magnetic state, no, it is not at all related. Excited state means that is a different thing which is not related to the NMR. Okay, only the spin state. At the spin state only we are talking about this precessional frequency. So at this state the natural frequency is become to the precessional frequency. So the terms like Larmor frequency, some Larmor equation, it is also there related to the NMR. We are going to see that in the spin state only we are going to observe this precessional frequency. Okay, let us move to the next question. NMR signal is obtained when? Yeah, just now we have discussed. So let us see the options. Applied frequency whenever it is equal to the radio frequency. They are asking applied frequency equal to precessional frequency, precessional frequency equal to radio frequency, precessional frequency equal to microwave frequency. Nowhere option D is the wrong answer. Precessional frequency, radio frequency, this is also wrong answer. So when applied frequency equal to the precessional frequency, radio waves are having some frequency. Okay, so then option A is also wrong answer. So automatically the option B, applied frequency, when it equals to the precessional frequency, then only the absorption of the radiation it is going to takes place. Next question, solvent used in the NMR spectroscopy should not contain. Okay, actually the question is somehow whether it is a proton NMR or carbon NMR, we are not going to use the solvent which is having a proton. Okay, so deprotonated solvents we have to use in the NMR. Hydrogen should not be there. In the proton NMR, what we are going to do? We are going to determine the number of protons. So if the solvent itself is having the proton, means it's useless. Definitely deprotonated solvents only we have to use. So should not contain hydrogen atom. So this is the right option. Okay. Helium, sodium, lithium, all these are not relevant. And next the question related to which of the following, again solvent only, is used in the NMR spectroscopy. Okay, solvent, which type of the solvent they are going to use? Carbon tetrachloride, deuterium oxide, CdCl3 and methane. Okay, so if you are seeing about the solvent which is not inert in the nature and it should not react with any type of the compound. Okay, so deuterium oxide, D2O, generally it is also preferred one, but CdCl3, this is also a solvent. Methane means CH4, it is there. Okay, CD4, deuterated ethane, this is also going to be used. So this is also right option, this is also right option. Deuterium oxide means D2O. CCl4, nowhere it is related to the hydrogen. So that is also going to be the correct option. So A, B, C, actually these three are going to be selected as the correct options, but not the D. Okay, might be the question is which of the following solvent not used in the NMR spectroscopy. So methane, it should not be used. Next question, which of the following is not the property of the solvent used in the NMR spectroscopy? Okay, so not the solvent property. The solvent should not possess that. What is that property? Chemical inertness, dipole moment, magnetic isotropy, volatility. Actually whatever the solvent it is there, it should be volatile in the nature. Okay, and chemically it should be inert in the nature, as well as it should not possess the dipole moment. It should not cause the change in the dipole moment. Only the nucleus has to change its, okay, but not the solvent. So that's why B, it is going to be the correct option. Next, electromagnetic radiation is supplied at which frequency range? Okay, the range of the frequency of the radiation. So we are giving radio waves as energy, but at which frequency we can produce that? Radio frequency generators are there. So at which frequency we can able to operate that? Let us see the given options. Actually 1000 to 2000 megahertz, 60 to 100 megahertz, 4 to 900 megahertz, 4 to 100 megahertz. Actually all the NMRs, proton NMR or carbon NMR which you are going to use, they are going to be used from 60 to 900 megahertz we can use. But theoretically if you are talking about that 4 to 900 megahertz, it is the theoretical value. 4 to 900 megahertz is the frequency range. So 4 megahertz also instruments can be operated, whereas 60 also you can operate, 80 also you can operate, 100 also you can operate, whereas 400, 900, all these instruments are also available in the market. Okay. So electromagnetic radiation is supplied at which frequency range? So the optimal range for the NMR is 4 to 900 megahertz we can use. So here the options 4 to 900, option C. 4 to 100 it is also there, 60 to 100 it is also there, 1000 to 2000 it is nowhere it is related. Okay, but you can operate at this range, not only this range. Okay, so this is a correct option you can select. Let us move to the next question. Which of the following is the expression for the gyroscopic? Okay, gyromagnetic ratio. Oh, already we have seen one formula for the angular momentum, magnetic momentum and angular momentum related to the nucleus. We have come across one question related to that. So here again they have asked expression for the gyroscopic ratio or gyromagnetic ratio, whatever it is, the formula. So if you know the formula only, you can answer this. Options, if you see also, let us have some what is actually gyromagnetic ratio. Let us see some of the definition, theoretical aspects for this gyromagnetic ratio. Okay, so this gyromagnetic ratio, it is nothing but a fundamental physical constant. It is going to be represented with the symbol gamma. Okay, so it is a physical constant value which is unique to each type of the nucleus. That means for a proton it is going to be a fixed value will be there, for C13, for P31, or like that. For each atom, for each isotope, it is going to be a fixed value, gyromagnetic ratio. Okay, so actually what it determines, it is a sensitivity. It is sensitivity of the nucleus, that is it is applied on the applied magnetic field. We are applying some of the magnetic field and we are giving the radio frequency as energy to the molecule, right? So whenever we are going to give these two, the nucleus has to take that when applied frequency equal to precisional frequency. Okay, so this gyromagnetic ratio, it is going to be sensitive to that magnetic field, right? So whenever it is directly related to the Larmor frequency, that's what precisional frequency I told you, that precisional frequency, it is going to be calculated as Larmor frequency, which is the frequency at which nuclear magnetic moment, whatever the moment it is there, angular moment. Okay, so that presses around the applied magnetic field, the external magnetic field, whatever we are going to apply. So due to that, you are going to see the frequency, that is nothing but the Larmor frequency. Okay, so based on this, all these frequencies, external magnetic field, okay, so the absorption of the radiation, it is going to take place. Then you are going to see the different atoms are going to give the peaks at different chemical shift values. So the chemical shift, whatever we are going to observe in this NMR, it is going to be influenced by this local magnetic environment. Okay, due to the delocalization of the electrons or pi electrons, whatever it is there, due to that magnetic environment which is going to be taken up by the interior part of the nucleus. Okay, thereby you are going to see the different chemical shift values. So this due to that chemical shift values, you are going to calculate the gyromagnetic ratio, because it is going to cause some of the magnetic momentum. Okay, so the precise, whatever the measurement it is there of this ratio is essential for the actual interpretation of the NMR data. And because of this chemical shift values only, we will come to know that which type of the carbon atoms are there, or hydrogen, number of hydrogens are there. Okay, so related to which environment it is there. So this gyromagnetic ratio, because of this you are going to see in any type of the nucleus while it is going to spin. Okay, so I think it is visible now. Yeah, it is related to the relative sensitivity. Okay, it is going to cause this very sensitive ratio, very physical value. It is going to be specific to the particular nuclei. So it is going to be calculated by using the formula, that is gamma. It is going to be represented with the gamma. So gamma equal to 2 pi divided by H. So this magnetic moment, it is going to be represented as mu divided by I, spin quantum number, it is going to be there. Okay, here P is nothing but, this is related to gamma equal to mu by P actually. Okay, so this P is nothing but the angular moment, gamma is the gyromagnetic ratio, angular moment and magnetic moment we are going to see. Okay, so this gyromagnetic ratio, it is going to be calculated by using this formula. So whenever the spin quantum numbers are there, we are going to take it into the consideration, plus half or minus half, these are the normal spin quantum numbers, but some of the nuclei are going to exhibit, we have seen already, minus 3/2, minus 5/2, plus state, minus state, anything you are going to observe. Okay, so this is the gyromagnetic ratio formula. Based on that, we are going to calculate for each specific molecule, it is a constant value. So from this constant value, you will come to know which type of the molecule it is. Okay, so then if you see the options they have given, which of the following is the expression for this gyromagnetic ratio? So gamma equal to 2 pi nu divided by Hi. Okay, so that is a formula related to that. Option C is the right answer. Next question, NMR spectrum, the number of signals represents. Okay, so majorly in the competitive exams, from the NMR topic, if you are getting any question, means that is related to the number of signals only. How many number of signals it is going to give in the NMR spectroscopy. They will give you one structure of the molecule or some of type of the name of the molecules also they are going to give. Let us see the options they have given. Number of different sets of the equivalent electrons in the molecule. Nuclear magnetic resonance spectroscopy. Nuclear magnetic, majorly it is going to deal with the nucleus. So here they are telling about equivalent electrons. Let us see the another options. Number of different sets of equivalent protons. C, number of different sets of equivalent positrons of a molecule, or none of the above. Okay, so none of the above means it is going to be wrong answer. So positrons you are not going to get it from the NMR, and electrons also you are not going to get it. So if you are getting the electrons means that is called as ESR, electron spin resonance spectroscopy. Okay, in the NMR you are going to get the this protons, proton NMR, whatever it is we are going to study. Okay, so option B is going to be the right answer. Next, last but one, number of signals in the acetone molecule. Okay, so acetone molecule, that means if you are going to observe the structure for this CH3 acetone, you are going to see, right? So number of signals we are going to see for the acetone, CH3COCH3, that is the chemical structure, because of the non-equivalent protons, right? We are going to get the different signals, position of the hydrogens we will come to know. And here in this, if you see the signals related to the acetone, CH3COCH3, means you are going to see the these three hydrogens are going to be equivalent. Okay, so that's why you are going to see the only one signal for acetone molecule, because with respect to this you are going to see the equivalent hydrogens on one side, and with respect to this you are going to see the equivalent hydrogens on the another side. So only one signal you are going to observe for this NMR. So if these are the non-equivalent hydrogens are there, then you are going to observe the based on the neighboring hydrogens, different types of the signals are there. Okay, so this is actually related to the proton NMR. In proton NMR you are going to see the one signal, and carbon NMR, that is going to be the another different thing. Okay, next, number of signals in the cyclobutane molecule. Okay, this cyclobutane, it is also there. So in this also mostly you are going to see the one signal only, because cyclobutane, if you are going to see, this is also equivalent hydrogens only it is going to possess, no non-equivalent hydrogens are there. So for that purpose only you are going to observe only one signal. If there are any type of the non-equivalent hydrogens are present, then definitely you are going to see the different signals. Okay, so these are some of the MCQs related to the NMR spectroscopy. Some more topics are also there, and this is actually we considered as a part 1 of the NMR. Only basic things we have discussed. We are going to learn about more number of MCQs in the more upcoming videos. Okay. Thank you students. Thank you for attending. Please subscribe to this GDC English channel, and try to attend the classes related to this Target Pharma 360 as well as Pharma Thunderstorm also. Thank you students. Good evening and good night everyone.